that knowing the asymptotic of the logarithm of the Schur generating function, namely knowing three conditions, 1 over n d dx1 to the a of the logarithm converges to some number ca, then d dx1 to the a times d dx2 to the d of the logarithm converges to some other numbers dab, and the derivative of degree 3 or greater, so product d dx a of the logarithm sp converges to 0 if this set has at least 3 elements. So these are all derivatives which are computed at the point 1. So that's the point when all the variables equal to 1. So these are 3 conditions, taking about first derivative, second derivative, and derivative in 3 variables. And we get 2 countable connections of the numbers. OK, let's try that. All x's is equal to 1, all x's are equal to 1, all x's are equal to 1. And then these 3 conditions are equivalent. So that is if and only if statement. To the 3 conditions on their random variables pkn, and these 3 conditions were the following ones. So there was a limit, it then goes to infinity 1 over n pkn is given by some numbers, pk. Then the covariance of these guys, so that is expectation of pkn pmn minus expectation pkn times expectation pmn. This was convergent to some other set of numbers. Let's call them covariance of k and m. And the last condition was that after we subtract the mean, so pkn minus expectation of pkn, then the collection of these random variables for all k together becomes asymptotically Gaussian. Jointly, I mean. Asymptotically. Gaussian. OK, so this is a general statement, and we also have a formula. Formulas which collect this countable sequence of numbers with this countable sequence of numbers. So these are finite formulas. So last time we were mostly concentrated on the law of large numbers, so on the connection of CAs to PKs. And from that we deduced, for example, the Arctic circle for the Aztec diamond. Today we want to go the next step. We want to understand what these covariances, what do they tell us? So what can you extract from knowing the covariances? So let me repeat the formula that I wrote last time, that this covariance k and m can be computed as coefficient of z inverse w inverse over the sum z to the a divided by w plus a plus 1 squared plus sum dab a minus 1 factorial, b minus 1 factorial, z to the a minus 1, w to the a minus 1. That's not it. There's also 1 plus z over z plus 1 plus z multiplied, let's call it q of z to the power k. And there is 1 plus w over w plus 1 plus w q of w to the power m. And finally, this function q that is generating a function of c's. So that's q of z is equal to the sum ca z to the a minus 1 divided by a minus 1 factorial. Okay, that's a statement that we were discussing last time. So it's important to remember that this is, if and only if statement. Although we will never use it in these lectures, we will only use it in this direction. But actually, knowledge that it also works in other direction, it helps in many problems. Okay, now, if really we want to concentrate on this part, on the part about Gaussianity and central limit theorem, then it's convenient to have some analogy with classical statements of one-dimensional probability theory. So let's develop this analogy. Now, if you just have random variables, one-dimensional random variables, maybe psi I, and you want to study, what's the asymptotic of these random variables, then what people usually often do, they compute similar things. So instead of Schur generating function, they compute just Laplace transform or characteristic function, you would say. So expectation of the exponent of Ix, it's better to have this j here, psi j, where I is imaginary unit this time. And, well, if you know something about this thing, so if you know that 1 over I ddx, let's call it phi, of logarithm of phi at point x equals to 0 converges to some constant c, well, then this means that you have a convergence of expectations of these random variables, because this derivative is precisely expectation of your random variable. So this is related to the law of large numbers. Now, on the other hand, if you know that the second derivative of this thing, so 1 over I, not 1 over I, just minus 1, second derivative of this thing, again at x equals to 0, converges to some other constant, call it sigma squared, then you actually know what's happening with covariance of these random variables, because this second derivative precisely gives you just variance of this random variable psi, if you make a small computation here. So if, in addition, you know something about larger derivatives, if you know that ddx to the power k for k greater than 2 of logarithm of phi x equals 0 converges to 0, then what you can understand is that your random variable psi j becomes Gaussian as j goes to infinity. So this is asymptotic Gaussianity. And the way to see that is, of course, well, if high derivatives of the logarithm are 0, then it means that the phi approximately look like exponent of some quadratic function. And that's precisely Gaussian random variable. So you see clear analogy here. So you have three conditions. One is responsible for the law of large numbers, another is responsible for the variance, and the third one is responsible to Gaussianity. And here we also have these kind of three conditions which appear here. Okay, now if you think further, now where are these techniques used usually, the convergence of the characteristic functions? Well, people usually use it in the context of just sums of independent random variables, just classical central limit theorem. Now, what is known in that context is that the limit, when you sum in independent random variable, is somewhat universal. You have Gaussian law, but in addition, there is a one-dimensional object which appears here, which is called Brownian motion. Well, really, if you consider almost arbitrary random variables, you look at their sums, then the trajectories will converge to the Brownian motion. Now, the question that I want to address now is, okay, what's happening in this two-dimensional setting? Now, we see that, again, under weak conditions, you have convergence to some Gaussian object. Now, what is the analog of the Brownian motion in this setting? That's what we want to address. And the answer will be that in this, I would say, two-dimensional setting, universal object which replaces Brownian motion is so-called Gaussian free field. Well, we will not see universality today, but we will at least try to see that in the simplest possible example of the Aztec diamond, these formulas somewhat immediately, well, through some computations, leads to understanding that there is a Gaussian free field which governs some fluctuations of this Aztec diamond. Okay, so let's recall the setup of the Aztec diamond. So what was happening there? So we had our Aztec diamond. Had two coordinates here. Let's call them x and y. And it was of size n. And we were looking at the slices at distance k from this side. And we were looking at the particles on these slices. And we were using extensively the fact that the Schur generating function of these guys is equal to the product 1 plus xi over 2 raised to the power n minus k. I goes from 1 to k. Now, as soon as you know that, well, you start taking derivatives, compute these CAs. DABs will turn out to be 0 just because the logarithm is the sum. So you just directly apply these formulas, and you get some answer. So if you just do it, here's a theorem that you get. Let's go here, theorem. Well, let's introduce notation P, Y, and M, which will be the sum over y times n particles in this row. So we set k equal to y times n. And we're summing over positions of these particles. Well, we take the position of ith particle on the row yn, we divide it by n, and we raise it to the power n. So these are the same power sums as before. So there is a small difference here. So the difference is that, well, now we divide by n. So before, when we had k particles, then we were always normalizing. Well, here we had large n particles, and so we were normalizing by large n. If you want to see some two-dimensional object, then it's a little bit inconvenient, just because there will be different number of particles in each row, and you will be normalizing by different numbers. We don't want to do it. So let's fix one normalization. So everything will be normalized by the same thing n. And so, other from that, that's the same thing that we had before. So if we have these notations, then these guys, P, Y, M, minus their expectations, are asymptotically Gaussian. And so everything is defined by their covariance. And the covariance for 0 is smaller than y1, smaller or equal than y2, smaller than 1. We can write down the covariance as the following thing. So the covariance of P, y1, m1, and Py2, m2 converges to a double contraintegral expression. So it will be y1 to the m1, y2 to the m2 divided by 2 pi I squared. And then there will be a double contraintegral. So z will be contour of radius epsilon. W will be contour of radius 2 epsilon. And then there will be z plus 1 over z plus z plus 1 over z plus 2, 1 minus y1 divided by y1 to the power m1. Then the same expression in w and related to m2. One minus y2 divided by y2 raised to the power m2. And finally, there will be dz dw divided by z minus w squared.
So the order of integration.
Yes, so that's important here. So y1 is smaller than y2. And this reflects to the fact that z is smaller than w here. Now, okay, so in which sense do we already know? Which case of this theorem do we already know? So I claim that yes, when y's are equal, then that's precisely this statement, nothing else. Because here d is our 0, this is 1 over z minus w, and that's, you recognize the same expression there. I just plugged in the expression for q of z. Now, when y's are not equal, then it is something a little bit new. Because now this is telling us something about the covariance for the particles which live on different lines, which in principle we didn't have it before. Okay? So I will not give a full proof of how you really understand that you can work not only with y1 equal to y2, but actually y1 smaller than y2. Let me just give you one idea which shows you how to even start thinking here. So if you remember, when y's were equal, then the main idea was that we have our differential operators, we apply them for Schur generating functions. Okay, well done. Now, what do you do when you have several slices? Well, the idea is, of course, that you need to extend somehow your Schur generating functions so that they can work in higher dimension when you have several collections of particles. So luckily here, the structure is very nice. So it will be particularly simple to do this operation. Okay, so let's erase something. So I don't think that we need this formula anymore. Okay, so this will be elements of this proof of this theorem. And then afterwards, I will give you interpretation of this theorem. Okay, so remember that we know lots of things about the structure in the Aztec diamond. Namely, what we know is that it is a Schur process, that you can represent it by a sequence of Young diagrams linked by specializations. One is alpha, another is beta, etc. So up arrows correspond to alpha specialization, and down arrow corresponds to beta specialization. Now, what we figured out 2 lectures before was how do you start with a Schur process and how you understand the law of a single Young diagram in this Schur process. So maybe the law of this lambda 2. And if you remember, the idea there was quite simple. We were telling, OK, in order to find the law of lambda 2, what do we need to do? We need to sum over all Young diagrams which sit here. So the Schur process is the law of 1, 2, 3, 4, 5, 6, 7 Young diagrams, and we need to keep only one of them. So we need to sum over all other guys. Now, the way to do these summations, if you remember, was to use skew-Cauchy identity, which was telling you that if you have something like, you want to sum over this guy when others are fixed, and instead you can replace this summation by another summation, which is pictorially can be shown in this form, meaning that the new Young diagram appears here, but now this new Young diagram will be smaller than this one. And because of that, it will be, again, empty Young diagram, and this simplifies the sum. So do I need to repeat any details of that argument? Or not really? OK, hopefully not really. OK, now you can use the same idea for their several Young diagrams. Now, if you do that, and if you now in this arrow, in this array of Young diagrams, you want to find the joint distribution of maybe lambda L1 and lambda L2, then doing exactly the same trick, you can reduce everything to the following picture. To saying that you have here some specialization alpha equals 1 to the L, which is a specialization in L alphas equal to 1. Then there is a next one, which is a specialization in L2 minus L1 betas. Beta equals to 1, this power. And there is some mu, which is still floating around. And then there is again some numbers of alphas. 2 minus L1. And finally, there is the last one, which is beta equals to 1 and minus L2.
I know that this is annoying, but there are plus 1, minus 1, depending if you are looking to 1.
Yes, I agree. Let's look only on the top ones. Yeah, OK. Maybe there is plus or minus 1 somewhere here, depending on. It will not be important at all in the answer. So let's just ignore that. OK, so do I need to remind anyone what this picture means? Don't be shy. If I need, I can remind it. OK, let's assume that I don't need to remind anyone. OK, now we want to understand the joint law of this guy and this guy. So how do we do this? Well, first observation is that really there is a Markov chain. So the transition from here to here, well, this joint law of this thing can be treated as a Markov chain. This maybe trivial statement is essentially tells nothing when you have 2 times and saying that you have a Markov chain. Well, this doesn't tell us anything actually. But we want to develop something general which will work also if there are not 2 of these guys, but maybe 10 of them. Then knowing that you have a Markov chain will mean something. So, well, we will also look at this Markov chain in this direction. So that will be our time. To be kind of going in the opposite direction to what is drawn on the picture. So, well, if we treat this as a Markov chain, then there is some transitional probability. P lambda L2 goes to lambda L1. Now, I claim that these transitional probabilities can be encoded in a particular simple way, again, by using Schur generating functions. So here is a statement. So if you take normalized Schur polynomial in L2 variables, x1, x, L2. Excuse me?
Divide by the specialization.
Yes, I will divide it again. I'm always doing that. So they're always normalized. If you take this guy, if you multiply it by the product 1 plus xi over 2 raised to the power L2 minus L1, so you still have L2 variables. Then you need to set some of them equal to 1. Namely, you want to arrive at L1 variables afterwards. So you will say that x L1 plus 1 is equal to 1, etc. X L2 is equal to 1. So L2 minus L1 variables are getting set to 1. All others still remain. Now, this is a symmetric polynomial in all variables. So after you set some of them equal to 1, this becomes a symmetric polynomial in a smaller number of variables. And at this point, you can decompose it in the basis of Schur polynomials again. You can say that it is sum over lambda L1 of Schur polynomials as lambda L1 x1 xl1 as lambda L1 1 1. And the coefficients in this decomposition will turn out to be precisely our transition coefficients. So our transition probabilities. Lambda L2, 2, lambda L1. Okay, that's, let's call it lemma. That's the way to define your transitional probabilities. Well, you need a little bit to work a little bit because there is this mu here. So that's true that if there were no this part, if you would be only dealing with this alpha specialization, then really the transition between, imagine that here there is no this part at all, and this vertex is here, and you have only this. And the transition from here to here will be just by setting these guys equal to 1. And then there is definition of Schur polynomial, which tells you that, okay, that's the equivalent formula for that.
So it's a supersymmetric skew.
You can treat it like that. Yeah, you can treat it like supersymmetric skew thing, or you can, you can apply as before. You can apply, yes.
I was wondering if this relies on the fact that you are using a specific alpha specialization, so you add one variable at a time.
Well, here we already have, when we restrict to this thing, then we have more than one variable already. Because here we have L2 minus L1. Well, this L2 minus L1 is the same, like here. That is the same number that you set, number of errors which you set equal to 1. And there is another L2 minus L1 which appears here, and then it's the same L2 minus L1 which is here. So in principle, you can, you can split this. Yeah, in principle, you can. I mean, so the fact that all betas are equal to 1 is reflected by having here 1 plus xi. So you can have different parameters, and then these guys will be different. Not 1 plus xi, but some number plus xi. And also, you can be plugging in not once, but something else. And this will reflect the fact that maybe you plug in here not alpha all equal to 1, but maybe arbitrary sequence. So in principle, you could do that. Well, this technology that I'm speaking about is kind of adapted to plugging in ones because we are always normalizing by ones here. But in principle, nothing restricts you from trying to do the same with arbitrary specializations. Okay, now should I prove it or not? Let's have a vote. Who wants me to?
This is the definition of P.
No, the definition of P is as follows. So you have this Schur process, which says that the joint law of this guy, this guy, this guy, this guy, and this guy is product of Schur polynomial here, skew Schur polynomial here, skew Schur polynomial here, skew Schur polynomial here. Then you say that it implies that lambdas form a Markov chain, and I define by P transition probability of this Markov chain.
Okay, I see that there is a small argument here.
Yes.
Because it is symmetric, you have identified it individually.
So I claim that this is the same piece. Okay, so who doesn't want me to give a proof of this statement? Two people. Who wants me to give a proof of this statement? One person. Okay, 4. Okay, 4 to 2. Others are sleeping.
I have just one question. Here you have L2 larger than L1. You could have a situation where
well, the order is important. So you can have more guys, but it's important to have some ordering, like from left to right. And you're right that kind of the length of this Young diagram is decreasing. So if you want to have yes. So
it could be also some other situation, some other process.
it could be.
Is it specific to your Aztec diamond?
Yeah, that is something specific to Aztec diamond. I agree.
In general, there is no reason for
yes, although, the general something of this sort will also hold. I mean, it's a little bit different. These identities adapted to the Aztec diamond. That's correct.
But I think the whole is what was inside, which are specific to identity.
Yes. Yeah, that's true. Well, but in principle, you can be multiplying here by something else, not by 1 plus 8, but some complicated function. And when you expand everything, you will get something of this sort, maybe a little bit different. Okay, so let's prove it then. So we want to understand why multiplying by these guys gives precisely the beta specialization here, because alpha specialization is appearing from the specializing the variables pretty much by the definition. So we want to prove the following thing, that S lambda of x1 xl2 divided by S lambda once, if you multiply it by the product of 1 plus xi, the L2 minus L1, divided by 2 as usual, then you get, and if you expand it back into Schur functions, the sum of S mu x1 xl2 divided by S mu once, then the coefficients of this expansion, let's call this P or beta lambda 2 mu, then these coefficients can be identified, well, up to some trivial factors with a skew-Schur polynomial S mu over lambda. Beta equals to 1, 2 minus L1. Because that's what we want. We want to somehow understand how this arrow appears. I claim it appears just because these coefficients, well, in fact, each coefficient of this kind, if there were no these denominators, no S mu, no S lambda, then I claim that the coefficient will be precisely S mu over lambda. And why is that? Well, if you think about it, then this is precisely the same skew-Cauchy identity that we had before. Because, okay, forget about this denominator, then it is S mu multiplied by S mu over lambda. So you can change summing over mu larger than lambda to summing over mu which is smaller. And here, it will mean that you are smaller than empty set. And so summation will be restricted to only one element. And this one element is precisely written there. And the factor, which is here, is precisely in this skew-Cauchy identity. We had some, one of the sides was multiplied by some product of 1 minus xi yj's, which in turn, in this case, turns into this object. So that's pretty much how the proof proceeds.
But there's a denominator. There's S mu.
Yes, exactly. So this thing, in fact, is equal to this S mu over lambda multiplied by this guy and divided by this guy. So that's the final formula for this thing.
Right. That is true.
Okay, so I don't know whether more people understood the proof after I gave it, but hopefully. Okay, so now let's believe in this statement. Like, what does it tell us philosophically? Well, it tells us philosophically the following thing, which you can now consider it in very abstract setting. So you have just some probability distribution here, and the transition from the probability distribution here to the probability distribution here with respect to transition probabilities for Markov chain can be written in a very short way on the language of these Schur generating functions. Namely, you take some probability distribution here, you take a Schur generating function, now you multiply a Schur generating function by this term, and you plug in some of the variables equal to 1. And then you get Schur generating function on this level. So all the thing is encoded by simple operation on the Schur generating function. And that's maybe the most important idea here. And the Markov chain just becomes an algebraic operation on Schur generating function.
But in the very first few lectures, maybe the first one, Bufetov was showing a method that was done by Johansson, I believe, in which he was doing the recursion for showing the genetic function that is not dissimilar from this one, in which h2 minus h1 is equal to 1.
Yeah, it's very close to in a spirit to that, because that's the same kind of the same thing was appearing there. So in a spirit it was almost the same. That's true. Okay, now important corollary of this computation. That's the main thing why I was discussing it at all. So let's call it proposition. The corollary is that if you want to compute expectation of P L1 M1 times P L2 M2, okay, let's say multiplied by the n to the power L1 plus L2. In other words, it is a power sum which is a sum of the coordinates of this guy raised to the power m. And that's a power sum which is the sum of the coordinates of this guy raised to the power m. So the same power sum as we had before. Then I claim that again you can write it by applying your operators. Namely, that will be the following thing. So first, you apply your operator dm2 to the Schur generating function which you get at time L2. So that's a Schur generating function for lambda L2. And as we know, that is again some power of this guy, 1 plus xi, product of 1 plus xi over 2 raised to some power. That's the first step. Then you take the result, you multiply it by the product of 1 plus xi over 2 raised to the power L2 minus L1. Then you take this thing and you set the variables from L1 to 1 up to x L2 equal to 1. After that, you apply your operator M1, dm1. So this one was acting in L2 variables. This one is acting in L1 variables. So that acts in L2 variables. This acts in L1 variables. And afterwards, you set all the remaining variables equal to 1.
You don't multiply by anything else?
No.
What's the question?
What's the question
It's a
again?
ludicrous question. No, but so after you did dm2, you multiplied by something, but then after you do dm1, you don't multiply by something.
No, that's it.
Well, if you multiply, you then specialize everything to 1.
Yeah, it doesn't matter. Yeah, exactly. It's,
You multiply because afterwards...
yeah, it doesn't help. Okay, so let's try to understand why that's true. So remember what were our operators? So the operators...
Instead of the y, you could just multiply that for I not larger than L1, because the other ones just specialize immediately.
Oh yeah, that's true.
In that case,
Yeah, it makes sense only to multiply those which will remain after we specialize this thing equal to 1. Okay, so remember what were dm's? So dm was product psi minus xj inverse times sum xi di to the m
the inverse
times,
on the other side of the bracket.
times xi minus xj. And the beauty of these operators was that their eigenfunction was precisely a Schur polynomial and eigenvalue was a power sum. Now let's see what's happening here. So you start with your Schur generating function, which is the sum of the probabilities of L2s multiplied by the Schur polynomial. So that is the sum. Let's write it here. So you start with the probability of lambda L2 times Schur polynomial. You apply your operator once, you get an eigenfunction, which is precisely the power sum. So you get here sum of lambda E L2 plus L2 minus I raised to the power M1, M2. Now afterwards, you do your operation here. You plug in some variables equal to 1 and you multiply by this guy. Now what it means, due to our property, is that the result will be, let's say what it will be, L2 plus L2 minus I. It's like Li plus n minus I. It's lambda I. So we have here L2 coordinates. So that's our usual guy, lambda I plus n minus I. Now n, number of variables, is equal to L2. So that's all what happened. Okay, so now you apply your operator, and by the definition you get a double sum, sum of lambda L1, lambda L2. Okay, what is being summed here? So this guy is still here. So let's. So this guy remains here. Now there will be transitional probability, and this guy also remains here, P lambda L2, and then there is a transitional probability lambda L2 to lambda L1. And finally, there is a Schur polynomial now corresponding to L1. Yes, lambda L1 of x's divided by s lambda L1 of all ones. This is just because of this property, because we know that that's the property of our transitional coefficients. Okay, now at this point, you apply another operator, which gives you eigenvalue, which will be the power sums now in these guys, in lambda L1. And then you set all the variables equal to 1, and this factor disappears. Okay? So in the end, you get, this statement. And similarly, you can generalize it to, arbitrary. So this is how you compute the joint moment, the product of the power sums on this level and on this level, just by using that formula. Now you can generalize it to several slices and several guys. The only important thing here is that now the ordering is really important. That you really started with M2 L2, then you move to M1 L1. And that's precisely why in this formula also the order is important. Really, this order is just born from this order of applying differential operators. Because they are now acting different number of variables, don't commute anymore, so this becomes important. Okay, given this formula and its generalization for arbitrary many Young diagrams, now all the arguments are the same. So really you do the same. You compute the moments using these things, and you start looking at the combinatorics of the resulting things. And I will not go further into details because that's computational. Well, instead, yes.
You are not going in the details for showing that the moments for the Q-bone they are small, or also for the
no, I'm not going. So this theorem formally was applied. You can apply it only for the case when you have only one Young diagram, so only one slice. Now I'm telling you that you can produce, exactly the same theorem, which will be working with several Young diagrams linked into a Markov chain. And the Markov chain will be nicely acting on the Schur generating functions like we have here, like multiplying some of those and setting the variables to 1. Now I claim that there is an exact analog of this statement now in the case when you have several Young diagrams. And the way to prove this analog of this statement is to observe that our trick with using differential operators still works.
So essentially you're telling that even for the formula for the variance, for the covariance, if you know how to do that at the same time, you just have to redo the same calculation while being careful.
Exactly. Exactly. There is no new ingredients. You just take the proof for equal times, and you replace, before we just had one operator times another operator. Now you add this thing, and you do exactly the same, like one line by line. And you get, the proof. Since I was omitting, details even in that previous proof, there is no way how I can, add some details here. Okay, so that's the reason why this theorem is true. This one. Now let's try to, say something. Let's try to say what this theorem really means. Let's erase it. Let's erase what? Okay, so the message. Let's erase this one as well. So the interpretation which I want to show is as follows. So I want to say that, okay, there is your Aztec diamond, there is this inscribed circle, and we know that fluctuations are only happening inside the inscribed circle because outside that everything is frozen and there is nothing. And I want to say that this theorem means that, that fluctuations inside circle converge to the Gaussian free field. So that's a statement that I will be trying to explain. Now we don't yet know what is Gaussian free field and what does it mean that the fluctuations converge, so I will need to decode all these parts of the statement. But from a mathematical point of view, this is just what I'm going to do, just interpret this formula. So if you're just caring about asymptotics, you can say, okay, and at this point, the problem is done, because you know the asymptotics of everything. But if you want some kind of philosophical understanding, what does it mean, then you want to have this. Okay, so what is the Gaussian free field? Let's first ask, who in the audience knows what is the Gaussian free field?
At which level of knows? Positive level.
Okay, positive density, but far from 1. Okay, so let me then briefly tell you the definition. So we will define the Gaussian free field with Dirichlet boundary conditions. In the upper half plane. Well, so we will start with the most naive version of the definition. It says that this is a, this is a generalized function G from the upper half plane. We will call this U upper half plane to the real numbers, which is, which is Gaussian mean 0 and satisfies that the expectation of G of Z times g of w is equal to minus 1 over 2 pi I logarithm z minus w minus z minus w bar. And that we'll call covariance z and w. And z and w here are treated as just complex numbers in the upper half plane. So we live in the upper half plane u, and that's a complex coordinate here. This is just complex number. Yes, it is no I, just 1 over 2 pi. There's no I here. So that's a real number. Okay, so now it's my question to those who do not know what is Gaussian free field. So what problem do you see with this formula? If I define it in this way, that this is a Gaussian field, so Gaussian function with a covariance given by this formula. Do you see any problems? Yeah, Valentin knows a problem that, when z equals to w, this clearly goes to infinity. So, what is the variance of your field if if the formula gives you infinity? That is something goes wrong here, because if you have Gaussian random variable, then it cannot have infinite variance.
Anyway, you said that was a generalized function. You didn't say what.
Of course, yes. So the answer is in this, generalized, which I never explained what it means.
Sorry, inside the brackets you have z minus w. And
Z minus w bar, so this is a conjugate.
okay. There is no conjugate of z.
That's a conjugate, no? On the border? Yes. That's because that matches the fact that it's with Dirichlet boundary conditions. So Dirichlet means that it's 0, and indeed, at least when z and w are 0, then luckily this vanishes. So that is already good news. So the trick is that really is generalized. So it's not really quite a function. So you need to make sure that you understand the correct functional space where this thing lives, because it's not a usual function. So the next level of definition, a little bit less naive, but still quite naive, is telling you, okay, maybe we cannot make sense of the values of this function, but we can still integrate it. So if you have any test function f, then you can integrate pairing of your field g with this test function as an integral of g of z times f of z dz bar over the upper half plane. So this dz bar, this just means that this is two-dimensional integral dx dy. Just I wanted to write it in terms of the z coordinate. Well, if you don't know what is g of z, then you don't know what that is. But you can reverse the argument. You can say, okay, suppose that we know what that is, and then that will be a definition of g of z for us. So we will just define our field g by saying that whenever you take maybe smooth compactly supported function f, and you have, and you want to define this thing, then this is a bona fide mean zero Gaussian random variable. And what remains is just to say what will happen with covariance. So if you compute the covariance of two of these guys, g of f1, g of and f2, then the covariance is given by 4 integral f1 of z1, f2 of z2. Then there is this formula for the covariance, which I will not copy. Covariance zw, z1, z2. And then dz1, dz1 bar, dz2, dz2 bar.
Do you need a definition to say that all products decompose with the formula, or you don't need it?
Excuse me, what?
Expectation of gz1 dot gz4 is the sum of the three variables.
Yes, but part of the definition that these guys are Gaussian. So this kind of means that. Yeah. Gaussian exactly means that the higher moments can be computed by the big formula. So these are really Gaussian. Well, so if you believe in this definition, then this formula would be a corollary. Just because you take one expression of this sort, you multiply by another expression of the same sort, you get 4-dimensional integral from 2-dimensional integral. Then you take expectation, and when you take the expectation of gz1 multiplied by gz2, you get this covariance. On the other hand, you can treat this as a separate definition. So it's somehow useful to know another form of this formula, which says that the same thing is equal to their just double integral of f1 of z times delta inverse f2 of z dz bar. And who is delta inverse? So this is so-called inverse Laplace operator. So you take operator delta, which is ddx squared plus ddy squared. So this is the usual Laplace operator. And you invert it, namely that if inverse Laplace operator of f is equal to g, then this means that Laplace operator of g is equal to f. And additionally, you supply a boundary condition, which tells you that this g should satisfy Dirichlet boundary condition. So its value at the border of your domain, well, on this line, and also at the infinity, should be equal to 0. Again, now why is that equal to this? Well, that's a lemma. Maybe it's better to write it somewhere else. Let's write it here. So the lemma tells us that the double integral of f of z times minus 1 over 2 pi I logarithm z minus w bar dz bar is equal to the inverse Laplace operator applied to the function f and then evaluated at a point w.
I don't know if this is a question, but log of that ratio is a good one because you have this Dirichlet boundary condition on the axis and you have to take the mirror of W, which has a negative charge side and
Yeah,
in the full plane, it's just log.
That's true. That's true. That's how you can, arrive at this formula. Exactly.
I was wondering since a while, so that's why.
Yeah. So you kind of take the field on the entire plane, and then you do the symmetry trick. You're correct. So how do you prove this lemma? Well, what does it mean to check that this thing is this? It means that you need to apply the Laplace operator to this left-hand side, check that you get f. Well, applying Laplace operator here is really not hard because it acts in W, so you just differentiate this thing. So I will not show the details here, but you just do it, just differentiate under the integral. Well, look a little bit carefully on the integral because everything will be a bit exploding, and you figure out the thing. You also need to check Dirichlet boundary conditions, which is probably simple. So can we see that for the W, going to infinity and also sitting on the real line, this thing becomes 0. Can we see it? Let's assume the compact support. Let's assume smooth and compact support, for being simple. Yeah, exactly. So just this when W is real, then the denominator and numerator are the same. So this is logarithm of 1, so that is 0. So checking boundary conditions is a triviality here. Well, checking that Laplace operator X as we want is a little bit complicated, but not too much. Okay, so if you believe in this formula, then this transition is trivial because you just take the integral with respect to Z2 here, and you say, okay, and it becomes precisely this thing. Okay, so a little bit more advanced definition is telling you that actually you can pair your field not only with smooth test functions defined somewhere on the plane, but actually you also can pair it with test functions which are defined on some curves. Namely, if you have a so if you have some smooth curve, gamma, and a smooth function on that, which is defined on this curve, then you can define the pairings of your field with your function along the curve, well, in the most trivial way that you would guess, as an integral over gamma of g of z times f of z with respect to the length element of this curve. This is just usual Euclidean integral. And well, again, you can check the same properties that everything works out. So you again define this object actually by setting that we know how to compute its its covariance. And the main thing, of course, is that this formula for the covariance will never explode, just because the logarithm which you have in this thing, well, that is really an integrable thing. So as long as you multiply it by some smooth function, you will always be able to integrate it. There are no problems. So this singularity is integrable singularity, and that's why everything works here, actually. Okay, so what's good about this object? Well, one property which is good, and which is maybe one of the reasons why it appeared, that it has lots of symmetries. And the symmetries essentially appear because of the symmetries of the Laplace operator. So Laplace operator is invariant under conformal transformations. Not so many conformal transformations of the upper half plane, but there are Möbius transformations. And since Laplace operator is invariant under these Möbius transformations, so your field, the law of your field, will also be invariant, just as a corollary of this formula, because really nothing changes here. And another thing is that why do you treat it? Why could you even think about treating it as a two-dimensional analog of Brownian motion? Again, that's because of the Laplace operator, because as everybody probably knows, the Brownian motion is really related to the just operator of taking second derivative. That's how that's the generator of the semigroup related to it. And so this is really two-dimensional analog. Now, instead of second derivative, we have two second derivatives. And that's why we will find it in the Aztec diamond very shortly. So maybe we should have a small break. Let's have a 3 minutes break just to relax a little bit. And then we will find Gaussian free field in the Aztec diamond. Again?
This L1 and L2 is the
yeah.
It was a picture.
Yes.
That gives you the endpoint function.
Why do you think that's just covariance? I mean, I'm confused. So are you speaking about Gaussian free field now, or about Aztec?
No, about L1 and L2.
Oh yeah, but you can do it for any number of slices, and you just apply operators one after another in the in the time order.
Can you see that that's going to be the determinant of the two-point function? Yes, that's determinant, right?
I don't think it's determinant of two. In this sense, I don't think that's true. Why should it be so? I mean, asymptotically they are Gaussian, so that's a big formula which should be there.
No, what I'm saying is if you take n partitions in the Aztec diamond, and you look at where their parts are, the probability is a determinant of, it's an n by n determinant, right?
I mean, but each partition has, what do you mean by n by 7 determinant? Because each partition already has many parts.
All right, so you fix for each partition, you fix one part. You fix a particle here at some position.
Well, then I don't think it's...
I mean, it's a determinant point process.
That's true, but it is not quite visible here. I mean, that's...
So that's what I'm asking.
That's kind of different technology. I mean, it doesn't rely on the determinant point processes, and there is no a priori connection. I mean, it's kind of coincidence that Aztec diamond is also a determinantal point process. You can do all the same with, I would say, different boundary conditions.
No, yes, but
I mean, it's formally still determinantal point process, but people don't know anything about it.
So this technique will not allow you to compute a priori the endpoint function.
Even two-point function. I mean, it doesn't give you any correlation functions at all. It's not a technique about correlation functions. We never computed like two-point function. If you treat it as really correlation function, at 2 points. This is really a technique which is adapted to these global limits. So this Gaussianity, that's what you see here. This technique is, well, you can try to adapt it to the edge limits, maybe. I have some ideas how to do that. But for example,
from speaking to, I think, Alexey or Avisa, they told me, oh, you could definitely do that. But that was...
No, I mean, there is no... I mean, you can go to the edge limits, probably. I mean, but that's... I mean, for the Aztec diamond, of course, it's simple. But, if you want some generality, like, the theorem that I was showing to you, there are some. It's not non-trivial.
You have the Arctic circle as some sort of double critical point of something. So then you expand around that double critical point, whatever is in your contour integral.
Yeah, but the problem is that you need kind of contours. You need some, what does it mean, contours? You need to analytic continuation of everything. On the other hand, these Schur generating functions a priori, why should they even have analytic continuations to somewhere? So, but that's true. For the Aztec diamond, I can, show you the proof, which will prove Tracy-Widom law just, by operating with operators, with the same operators. But it will take some efforts, but it is doable. Yeah. For
any reasonable materialization.
For any example that you give me, I can work out this example.
Yes.
But that's a different thing, telling that you can work out each example, or telling that you have general theorem which covers them all.
Right.
So these are kind of two different things.
I see.
So let's continue, maybe.
I wanted to ask you,
Yeah.
how do you know that the Kirchhoff field exists?
Oh yeah. So that's so essentially, there is some kind of if you work through this, there are different approaches. So if you use our naive approach as defining Gaussian free field through these pairings, then you have some kind of Kolmogorov consistency theorem. Kolmogorov, that's how people define stochastic processes. They say if you have a consistent family of finite dimensional distributions, then it automatically defines you, in some abstract setting, the law of your object. Now, what you really need to check here is to check that, this definition of our covariance, that there is no contradiction there. That maybe, I define this covariance through that thing. Maybe if you take the same function here, it needs to be positive in the end. So, that's an abstract thing. So suppose that you want to define some Gaussian random vector. So when can you do it? So as long as you specified covariance, which is positive definite, then there always will exist a Gaussian vector with this covariance. Essentially because you can write down explicit characteristic function of this thing, maybe. Does it make sense? Okay, well, I mean, for Gaussian random variable, there is explicit formula for the distribution. For the Gaussian vector. So if you know the covariance, then you can just write down this formula, and that's your law, finite dimensional law. Okay? But the trick is that in order for the technology to work, you need to make sure that the covariance is positive definite. if it's not a positive definite matrix, then you will have something, but it will not be a random variable. It will be some mass.
Suppose you know your Gaussian field on this curve. Does it determine
On what again?
on any smooth curve? Here, because you could have some Gaussian field which are zero on any smooth curve, which are not zero.
Well, I would say that's a question about correct functional space, because you
You need some space and some
I mean,
adaptation and so on.
I mean, a priori, you can, for example, ask this equations about Brownian motion. If you just take a Brownian motion and you just specify its finite dimensional distributions, well, it's not enough because it might have many points of discontinuity. But what people do, they take, okay, there exists a continuous modification, which is nice, and then everything is uniquely defined. So for Gaussian free field, you can play the same game. You can say, okay, we first specify this covariance, and then we take some reasonable functional space, some Sobolev space, and you say, okay, now it makes sense as an element of this functional space. And at this moment, you know what you can do and what you can't do.
You have some survey space here, certainly, and you have to take an adaptation. So my question is about the smooth curve. They have to
Yeah, but the smooth curves, I think. I mean,
pressure on the smooth curve is singular.
Yes, but they uniquely define the covariance already. So by knowing everything on the smooth curves, you can reconstruct the covariance. If
Variance on the smooth
yeah, but if this
smooth curve, but the question is, can you find a non-trivial Gaussian field which vanishes on smooth curves? Integral on smooth curve.
can you find a non-trivial Gaussian field? Well, I mean, you can. On one smooth curve, on all smooth curves. On one, of course, you can just say that it's equal to 0 there. So it's about all smooth curves. I don't really know. Well, probably you can do something.
If you take two Peano curves interlacing, one red, one blue, and then value +1 and -1 on red and blue, this sort of example.
It's not Gaussian.
Yeah, you add it as a shift to the covariance. But yeah, I think
Let's continue. I mean, that's an interesting thing. I mean, that's true. But we don't know such. We don't need such details because.
Because you can
Yeah. We don't need it.
integrate over any function you like.
Yeah, exactly. So we will take it for granted that that it makes sense as an element of some nice functional space, and just use it. So our convergence will be in the end convergence of finite dimensional distributions. That's it. So we will not be claiming any stronger convergence. And that's, by the way, a very interesting question to understand whether you can do some stronger convergence, because people were able to find in Gaussian free fields. For example, Scott Sheffield and his team, they found all SLEs and all amazing objects inside Gaussian free field, which should mean that when you start from the Aztec diamond, you should also be able to find all these objects by some limit transitions. But that's some very strong topology if you do this limit transition. We have very, very weak topology essentially, just with finite dimensional distributions, and then it will work out. Okay, so now let's say what exactly is the theorem for this thing. So. But it is Gaussian function. This is Gaussian field, so this is a random field. And this is just a formula for the covariance of this field. This is the same as telling, you can define a Brownian motion by telling that it is one-dimensional Gaussian field whose covariance is the covariance between value at time t and time s is the minimum of t and s. This is just the same, same flavor of the definition. Okay, so let's define what is called height function of the configuration of the Aztec diamond. So the height
is the generalization of Dirichlet boundary condition
for the Brownian motion, yeah, you can do the same. If you think for the Brownian motion, you just need to consider Brownian bridge. If you look at the Brownian bridge on the interval of length 1, like from 0 to 1, so your Brownian motion starts at 0 and ends at 1. Then you can find precisely the same description. The covariance of this Brownian bridge will be precisely, well, this is called green function of the Laplace operator. That will be green function of the Laplace operator on this interval from 0 to 1 with Dirichlet boundary conditions.
Yeah,
So,
this is analog is on the half line. Because on the interval you have the double zero.
no, I think that's an analog of the Brownian bridge. That's my feeling. That the Gaussian free field is an analog of Brownian bridge, really.
When you said that the covariance is mean ST, that one is on the half line.
Yes, that's true. That's true.
When you say Brownian bridge, you mean Brownian motion between 0 and 1?
Yes. Well, it starts at 0 at 0 time and ends at time 1 again at the position 0. Okay, so let's define a height function of this Aztec diamond. So by the definition, h of x and y will be number of particles on line integer part of ny to the right from nx. Okay, let's draw a picture. So remember that we have particles assigned to our Aztec diamond, and they will be, there was growing number of these particles in rows. So in the first row there was 1 particle. In the second row there were 2 particles, and in the third row there were 3 particles, etc. So this height function was just counting, this number of particles in each row. So in each row, in this row, this was 1, because there is 1 particle on the right, and then 0 here, and there are no particles. Here, particles in different color. Here on this line it is 0, then 1, that's 2. Here it's 0, then 1, then 2, 3. So that is a function which makes it jumps along the section precisely at the times when you see a particle.
K and N are fixed.
So here we forget about k, now it's replaced by y. So n is the size of your Aztec diamond, and this is k, this integer part of ny, that is what was called k before. Because now we are on the line ny.
K is equal to ny.
Yeah, k is equal to ny, precisely. So of course, this height function encodes everything. Because if you know, your function, then you know where jumps are, and you know the positions of particles. Okay. Now, we defined so far our Gaussian free field in the upper half plane. And I was telling to you that something non-trivial should be happening here inside this circle. So we'll need some map which will map this circle onto upper half plane. It would be a map omega. In this case, this map is completely explicit. So point xy will be mapped with the root of polynomial z squared times 1 minus x plus z times 2y minus 2x plus 1 plus 2y equals to 0. So for each point xy, you have a quadratic polynomial. You can find a root of this polynomial, and that's what you should take. Well, we want this to be in the upper half plane. So in principle, quadratic polynomial either has 2 real roots or 2 complex roots. So 2 real roots is bad for us. That's not in the upper half plane. Two complex roots is good because that precisely means that one of them will be in the upper half plane. Well, when one situation changes to another, that's when discriminant is positive or negative. Well, luckily here the discriminant, well, I made my things at home. So if you compute this discriminant, then it's 2x minus 1 squared plus 2y minus 1 squared minus 1. That's the discriminant of this quadratic equation, which means that it's precisely smaller than 0 inside this circle. Which is good, because it means that really we have a map from the interior of this circle into the upper half plane by taking the root of this thing. Mm-hmm.
This situation is somewhat generic, right? This is what Kenyon called the complex structure of the...
There is some difference here. So if you go to the generic situation,
so for example, you would work also for hexagon, you would have a similar...
There is a tricky point here, which is the fact that Kenyon and Kunkov, they define complex structure really. Now we want something else. We want not just a complex structure, but we want a bijection to the upper half plane. So of course there is general, Riemann uniformization theorem, which tells you that as soon as you have some simply connected complex manifold, then it is the same as upper half plane. There is a bijection of that. But this uniformization map, that is something that is non-trivial thing. Well, maybe in this particular example it's not hard, but if you look at the maybe tilings of more complicated domains, then the complex structure is simple, but finding the uniformization map, that's additional effort, which is non-trivial.
Right. But what I'm saying is, let's say you change to the hexagon or to plane partitions. There you're going to have an equation in Z of degree 2. The answer to which is going to
No. So the fact that there is equation of degree 2 that is related to the geometry of this Aztec diamond. So if you consider...
Yes.
Yeah.
Hexagon.
Yes, but
partitions, it's also of degree.
Yes, but if you look at something like, I don't know, domain, like for the lozenge tilings domain of this form, and then it will be of higher degree.
But it will still have just two complex conjugates roots, and the rest of them are going to be real, right?
In the examples that we know, that's true, but that's a result of the method. That's not some general theorem. In principle, there is no guarantee for that. So let me tell you, there is a general conjecture due to Kenyon and Kunkov, which tells you that if you look at any tilings model, say domino tilings or lozenge tilings, then as soon as you know limit shape, they give some prescribed procedure how you define a complex structure on this limit shape. And then they claim that the fluctuations should be given by the Gaussian free field with respect to this complex structure. Now, what does it mean that it is Gaussian free field with respect to complex structure? It means that you should take uniformization map from that complex structure into the upper half plane and then make a pullback with respect to that thing. But this uniformization map, well, they tell nothing about it. They do not discuss it, I would say. Yes. The three-dimensional picture.
This one from the article, but knowing that it was the true things to do is an extra part.
Well, there is another, that's a theorem of Kenyon and Kunkov, which tells you that if you know the frozen boundary, in fact, you know the entire limit shape. That they have some procedure which reconstructs the limit shape, at least for the simply connected polygons, from knowing the frozen boundary.
But this is only for simply connected.
Yeah, this. Yes. This is exactly. But their conjecture about Gaussian free field is also only for their, for the dimer models.
But it could be true for the others.
Yes, that's true, but we don't know how to find complex structure. The conjecture, of course, everybody believes that, in any reasonable model of random surfaces, you should get Gaussian free field. But then, the devil is in details, because, what does it mean that you get it? They have more precise statement. They know what is a complex structure. And even that, you need to know something about this, this model, because hopefully I get to that in the very last lecture, that if you consider some cases of six-vertex model, then the fluctuations are not given for the Gaussian free field by some reason. But on the other hand, this artistic diamond, there is also a particular case of the six-vertex model, and here the fluctuations are given by the Gaussian free field.
So it is not that they are not Gaussian.
Well, there is one case, so there is a thing that we call stochastic six-vertex model that Alexey Bufetov already mentioned. This is a particular case of six-vertex model, and there the fluctuations are not Gaussian. So, we don't understand everything so far. That's too complicated. Well, I think that here you can see that x is equal to 1 is somehow special because the equation degenerates. So maybe that's x equals to 1? I don't know. Okay. Yes? Yeah. I think x equals to 1. Yeah.
X equal to 1 is boundary.
Yes, but it should be boundary because this map maps the boundary of the circle to the boundary of this domain. I finally can state the theorem. So the theorem tells you that h of x and y minus expectation of h of x and y converges as n goes to infinity to omega pullback of square root of pi times Gaussian free field. Well, what?
Sure, you don't have a Gaussian free field model. The critical exponents are different.
Well, it depends because again, that's a particular case of six-vertex model.
Yeah, the critical exponents are a function of the parameter delta.
Yes.
They are those of the Gaussian free field only.
I mean, again, even for the delta corresponding to the stochastic six-vertex model that we know, one of the graduate students of, working at MIT, he made some simulations which indicate that you can find some boundary conditions for which you will still have Gaussian free field. It's related to the behavior of free energy. Like you draw a graph of free energy, and if you are on a smooth point, then you expect to see Gaussian free field. If you are at some bad point, then not. And for the six-vertex model, there are ranges of parameters where where there are it has singularity, and then everything breaks down.
Actually, you could have also defined the Gaussian free field directly on the disk, then you will have even more.
Well, there is a tricky point that this map is not analytic. That is not something analytic. So essentially, by this map, we are defining complex structure in this disk. So it's not the same, complex structure that you will just take from the plane. So that's yes, and it's important that that's.
Just put x equal to cosine and y.
Okay, in this case, yes, but if you go in some more complicated case, then it will be changing. So what? Now let me comment really about this theorem. So what is universal here? What is not universal?
So it means that you cannot write the covariance as the green function inside.
Yes, because you need this complex structure. So the complex structure which is given by this map, you can say that this map defines a complex structure inside this circle, but it will not be a usual complex structure from the plane. So well, not too complicated in this case, but still it's some particular way of choosing complex structure. And in general, you can consider tilings of more complicated domains, then the complex structure will be becoming more and more universal. And in this sense, nobody is telling you that this map is any universal. What people believe is that you always get Gaussian free field, but this map, omega, well, it depends on your problem. Whatever you get, that you get. Now, what does it mean that you...
Maybe the reason the map is not, it's not holomorphic.
Exactly, yes.
So it's not the universal formalization.
Yes, exactly.
It's a different.
Yes, exactly. So map is holomorphic if you consider... So...
I think the difference between H and the average, don't you have to renormalize?
No, so you don't have. So H grows linearly, but their centered version grows not linearly. It grows just as a constant. Well, I need to specify what do I mean by this theorem, of course, because we have a convergence to some generalized field. Let me first give some author. So I think that first people who stated it in this form, it was Schitter, Johansson, and Jung. But it's a strange story that they, you can find the first version of their article in the archive where they claim that here's a sketch of the proof that you get Gaussian free field, but by some reason in the later versions they said, okay, there are too many details missing, and we decided now it's only conjecture, not a theorem. Anyway, so in our article with Alexey, this is actually proven. I mean, I believe that they just got lazy, but they could have figured out some old details, but I don't know, they didn't want to do it. In our article with Alexey, that is actually proven based on this method of Schur generating functions. Kenyon did it for Kenyon, the difficulty is that the Kenyon has a method which works only on the case where your limit shape has no frozen regions. So the fact that here we have the frozen regions, that somehow complicates the thing, because Kenyon has a method. That's a method which is used in many areas of this kind of statistical mechanics. He wants to have some discrete harmonic functions convergence to the continuous harmonic functions. But then the fact that the boundary condition which you should choose is not on the border of your domain, but somewhere inside and fluctuates, this complicates the things, and Kenyon is not able to access these cases in the end. So these are very specific domains for which Kenyon can prove, and not the simplest ones that you would take as an Aztec there. Okay, so let's have a proof. Well, first, we need question. No? So first, let's specify what do we even mean by this convergence. Since a Gaussian free field is a generalized object, probably we mean that there is a convergence of some test functions, and that's indeed true. And for our proof, we will take some somewhat specific test functions, so that.
What do you mean by test functions?
Well, as I just erased, you usually take your Gaussian free field and multiply it by some function and integrate the thing. Yeah, there was a pairing G, F. So we will be proving convergence of this kind of pairings.
Sorry, I understood that you define the Gaussian free field for any smooth F.
Yes. So now we will choose some particular F, and we will check, that there is a convergence to the thing that we need.
This function is not a mathematical object defined.
No, it is a mathematical object. So Gaussian free field is defined on any test function. So you take any smooth function and you integrate your field with this test function, you get a random variable.
Okay, but there is no definition of test. What a test is?
Oh, test is a word. That is a traditional word test function. That's a name. I mean, the question is the test. That's a name for the thing. Test function. Okay. Yeah. Yeah.
So it makes sense to call it test function, because what you do is that you take your G, where you don't exactly know what it means, but now you test your G on this function.
Yeah. Okay, so our test function will be as follows. So for each y, for each fixed value of y, we will compute and we will take a test function x to the k on this slice. So our test function will be not quite smooth function entire thing. It will be supported on a curve. So the curve is this section, or if you want, you can map it to the upper half plane. It will be something about our map, and then whatever you get as an image of this function x to the k here, that will be your test function. Yeah, this will be pk's in there. That's a connection to what we are doing, of course.
How do you know that this is
Well, I mean, polynomials are dense in whatever reasonable space you take, so yeah. So that's of course sufficient. But that is somewhat weak topology. That's correct. I mean, we cannot have, but this is enough to uniquely identify the covariance of the limiting object. Okay, so what do we need to do? We need to compute the integral from 0 to 1, x to the k, h of xy, and its expectation of h of xy, dx. And we want to show that this thing converges to the integral of Gaussian free field as we want. Okay, so the first thing that we do, we just start by integrating by parts. So if we integrate it by parts, and what we get is 1 over k2 plus 1 times integral from 0 to 1, x to the k plus 1, h prime xy minus expectation h prime x and y dx.
Because the boundaries, they are not zero, but they are deterministic.
Yeah, exactly. Boundaries are deterministic. Like we know that here, h is deterministic, and here h is deterministic. So the difference is of course 0. Yeah, just by the construction. Okay. Now the nice thing is that derivative of the height function, these are precisely jumps at the particles, and that's what we can work with. So this is the same as telling that it is 1 over k plus 1 times p y k plus 1 minus expectation of p y k plus 1. Pretty much just by the definition. Yeah, that is a power sum, the same power sum which is here. This one. So does everyone agree with this equality? Okay. Okay, so the first part is already done. We already know that these guys are asymptotically Gaussian. Okay, that's the theorem which is written there, which says, okay, these guys are Gaussian. So we already know that on our test functions, we have convergence to some Gaussian field. Okay? Now, what remains is to identify the covariance that you have with the covariance of our Gaussian free field. Okay, so they are Gaussian with covariance. Okay, for the covariance, we take that formula on the right and copy it somewhere else. I mean, it's something explicit, It's here, the map is explicit.
Yeah, but I mean, it's a curve.
Yeah, it's a curve. Yeah, it's some curve there.
Sorry, can you explain the passage between the second and the third line?
Yes, okay. So what is the derivative of h? Like h is a step function which makes the jumps at the particles of our configuration. So the derivative will be a delta function, sum of the delta function at the points of our configuration. And therefore, this is equal to that. What? Yes, exactly. That will be sum of the delta function at the points where a particle sits. When you integrate x to the k plus 1 with respect to the sum of the delta function, you get just the sum of these positions of these particles raised to the power k plus 1. And that's how you get it. Okay, so it's Gaussian with covariance given 1 over 2 pi I squared, L1 plus 1, L2 plus 1. So I have covariance between k equals to L1 and k equals to L2. These are two things for which you're computing the covariance. And here also we'll have y1 and y2. So then there'll be a double contour integral over absolute value of w greater than absolute value of z. Essentially, I'm just copying the formula from there. That that will be y1 z plus 1 over z plus 1 minus y1 z plus 1 over z plus 2 raised to the power L1 plus 1. Then y2 w plus 1 over w plus 1 minus y2 w plus 1 over w plus 2 to the power L2 plus 1 and 1 over z minus w squared dz dw. Yes, yes. So there was a factor y1 to the m1, y2 to the m2. I just put them inside here, and they canceled with something else. Okay, now the main observation is that you do to identify the formulas is that this thing is really closely related to this map. That's actually how the map appeared at first. So if you just look at this expression, then I claim, well, if you simplify it a little bit, then it's the same as 1 plus w divided by w, 2 plus w, w plus 2 y2. So I just simplified this expression. Nothing else happened. That's 1 plus w divided by w times 2 plus w and multiplied by w plus 2y2. I just simplified this expression. Yeah, I just put it into, into.
Go back to those philosophical questions we were telling after that post. We are not just using the integrals of the Gaussian field over any star, but we have chosen a fibration of the domain by horizontal lines, and we are doing covariance only by different factors. This is much less generic. Are we sure that this is enough to reconstruct?
Yes, it's uniquely because I mean, since we have arbitrary fibers, you can now integrate it with arbitrary function in this direction. From our theorem, you can get any test function which is polynomial in this direction and arbitrarily smooth in that direction.
So you don't really reconstruct all the curves. You just, from that, reconstruct two-dimensional test function.
Well, we have our one-dimensional. If you want, you can reconstruct two-dimensional. That's true.
The one-dimensional are intrinsically on the horizontal. You couldn't do a transversal one.
We don't do curves like that.
Yeah.
If that's, but again, the covariance is uniquely defined. If you treat Gaussian process as process with this given covariance, then we prove the convergence with the process with this given covariance, but in this weak topology. And the same thing, if you think about just the ordinary theory of stochastic processes, like people prove convergence of some stochastic process to Brownian motion. Now there are very different meanings on that. We are really working in the smallest, the weakest possible meaning, which is a convergence of finite dimensional distributions. You can prove that you have some stochastic process and its finite dimensional distributions converge to those of the Brownian motion. Well, of course, people also work with much stronger sense. They could develop, Skorokhod space of the continuous, test functions with certain topology, and then they prove the convergence of the law in this Skorokhod space. We are not doing that. We are doing, only finite dimensional distributions, but it is enough to uniquely define the limiting objects, nevertheless.
For example, if you something very concrete, if you do the construction of the particle once in a direction, say in this way, and once in this other way, then you would have had that separately. You would have a good control of this segment and on this segment, but calculation of the covariance.
Yeah, formally it doesn't follow. That's true that we can analyze separately this section and this section, but I'm not telling anything about the joint law along these two sections. That's true. Well, it's hard to expect that something will happen there, but formally the theorem doesn't tell anything about this joint law. Okay, so that is this thing. On the other hand, you can simplify this expression, and you can rewrite this expression as a formula for x as a function of z. If you rewrite it in this form, then the formula that you will get will be precisely x equals to z plus 1 multiplied by z plus 2y divided by z multiplied by z plus 2. So the same expression as there. That's, there's no miracle here. That's really how I came up with this map, just, look at this formula and then you try to identify the things. Okay, so it means that you can alternatively rewrite this entire thing as 1 over L1 plus 1, L2 plus 1, 2 pi I squared times double contour integral of x of z and y1 raised to the power L1 plus 1 times x of w and y2 raised to the power L2 plus 1. And then our old friends dz, dw, c minus w squared. Just rewriting in the notations given by this dependence of x on z. This equation is equivalent to this one. That's what I'm telling. Yeah, I'm solving for x. Yeah. Yes, y coordinate is fixed. So you fix y here, and you treat this as some relation between z and x. So you treat here y as a parameter, which is fixed. Then there's some. Yes, but it is fixed. When you integrate along our test function, then it is fixed.
No, but it's ordinary circle, but also in the other plane.
No, sorry. It is in this coordinate system. Yeah, yes. Y is fixed here. Okay. Now, let's erase something. Do I want to have everything? Believe in what? Yeah, then this you believe already, hopefully.
So this formula you could use it for case.
What again?
A more general formula that shall be true for general curves which remain one on top of the other all the time, but they are not straight. You could have.
No, of course, we have Gaussian free field. Formally, we can write, what should happen with any test function.
So you really say.
I mean, we prove it in the sense of weak topology, but we know everything about the limiting object. So I can write you the result for arbitrary test function. I just don't know how to prove it for arbitrary test function. But these test functions, they kind of dance in the set of all possible test functions. That's why I treat them as being, good enough. Okay, so now we deform the contours here. So we have here W contour and Z contour. We deform them in such a way that if we have, we have here Y1 and we have here Y2. So you can compute the images of Y1 and Y2 here. So you get two curves here. That's one and another. And let's also double these curves. So they were in the upper half plane, but let's reflect them to make them really like that. Okay. Since this map is really a bijection, well, we have not checked that, but you can believe me that with quadratic polynomials, it's not too hard to check that something is a bijection. Well, these curves were not intersecting here. They're still not intersecting here. So one will be inside another. And that's good because our integral was exactly treating two contours. One is inside another. Since this is an integral of analytic functions, you can freely deform the contours now so that one of them becomes one of the curves and another becomes another curve. At this point, you have this integral. This is z and w. I mean, this is a double contour integral in z and in w. Yes, but z was corresponding to y1 and w was corresponding to y2. So we deform Z contour so that it matches the image of the Y1 slice, and W contour so that it matches the image of Y2 slice.
Sorry, you are somehow extending your mapping to.
In the formula itself, there's no dependence on the dependencies.
Well, in the formula originally we had two contours, one is inside another. That's it. So we can deform them, however we like, and the result is still the same.
So at least from the outside, it has nothing to do with Y1 and Y2.
Yes, that's true.
You are identifying Z and W here in this integral as somehow.
Yes, we identify Z and W with these images there.
Originally, you were only this mapping was only in the upper half plane, so to have a close contour, you need to go also on the lower half plane. So
Yes, exactly. So I'm telling you that originally, of course, we are only at the upper half plane. So I'm telling you that let's deform the contour so that in the upper half plane they match this thing, and then you just continue them symmetrically. That's the contour deformation that we are using. Well, we are allowed to do any deformation we want. As Christian told there is no dependence on this choice of contours.
As long as we don't run into
Yeah, but there is that's some check, but you can check it here that it's not happening.
but here you are taking this definition of X, which is
No. In deformation of contours, we are not taking any definitions. I'm telling you that.
you need to know that we take orders from the analytic.
Yes, but look here. I mean, that's you are not sure whether it's an analytic function of Z.
At some point you are the analytic function.
Yeah, but in the integral there is no problem. I mean, look at the integral Z plus 1 over Z and Z plus 1 over Z plus 2. That's an analytic function of Z. Yeah, you should not run into minus 2 or 0. That's true. That is some check, but
there's no problem because
Okay. Okay. Yes. That is some check, but I will not do it here. Okay. So now you have the contour. Let's split now contour into 4 parts, because really in the end we want to be in the upper half plane, but now we have the contours which are going both in the upper half plane and in the lower half plane. So let's split it into upper part, then the lower part, and the second contour also. We split it into upper part and lower part. Okay? So split contours into 4 parts. Now we'll treat each part separately. And let's start with the simplest part, where both guys are integrated into the upper half plane. And let's make their, again, integration by parts. So each part integrated by parts. Okay, so you take this integral, you integrate it by parts twice in Z and in W. And in the end, you will take antiderivative of this 1 minus Z minus W 2 times. So what's happening when you take in 2 times antiderivative of Z1 minus Z minus W, first in Z, then in W? Yeah, you get the logarithm, and that's what we wanted to have. So you get that this integral is becoming, these guys are also getting absorbed. 1 over 2 pi I squared. It's not contour because it was only one of the 4 parts. You get x of z y1 to the L1, x zy2 L2. Then there is a logarithm of z minus w. And there is also dx dz and dx dw. So I integrated it by parts twice. Well, we had x, yes, we had x as a function of z here. When we differentiate, the derivative appears. Yeah, this is derivative of this function with respect to z, and that's derivative of this function with respect to w, given the I1, given the I2, or given y1, given y2. It is, but it was in denominator before, so it precisely cancelled out. Yes. And that's because we started from integration by parcels, so that's kind of...
So far, does it make a difference in 4 cases?
No, it doesn't. So what will be the difference in 4 cases, really? The difference will be that z will be replaced by z conjugate when we're in other case, because the contours are replaced by the conjugate ones. So it means that when we combine all four cases, and what we get is an integral only over these 2 guys in the upper half plane. So over this thing, this contour, and over this contour. But this time with, instead of logarithm of z minus w, we'll have some of the 4 terms. We'll get logarithm of z minus w plus logarithm. Well, there are different signs because they're oriented in different ways. So I will check plus minus because it's easy to get confused. Logarithm of z bar minus w, logarithm of z bar minus w bar. Okay, now if you carefully figure out what are the signs, then the result will be precisely twice logarithm of the absolute value z minus w divided by z minus w bar. Well, there is a choice of signs which gives you that, and I claim that that's precisely. Yeah, only one. That's true. Okay, so the result is that our covariance turned out to be this thing. Now I claim that that's precisely what we should get.
And no issue with boundary terms?
I mean, we started from really contours over the closed curves because of that all the. Well, they will disappear. I mean, okay, there is a, you check that. That's true, but it's no problem here. I mean, okay. There is a check that there are no boundary terms. I agree. Okay, now I claim that that's precisely what we wanted to prove. So why is that? Because I claim that that's precisely the covariance which you should get if you have a pullback of the Gaussian free field. Because what we are saying that the limit, okay, that's this thing combined into this logarithm of z minus w bar. That's precisely the covariance of the Gaussian free field, which we obtain here. And what are we integrating? We are integrating our function, because our function was x to the k here. So after we map here, it becomes x of z raised to the power, well, k was L1. And that's another function, again, x to the power L2. And what are these guys? Yeah, if you think really about what's happening with the integrals when you apply a map, there is always a Jacobian there. That's true. So when you make a change of coordinates in an integral, well, there is always a Jacobian, and that's precisely this Jacobian. So this formula is precisely what we wanted to get. So that ends the proof of our theorem about Gaussian free field. Okay, what's the time? Oh, that's the right time to finish. So let me just tell you a couple of words what will happen next. So at this point, we end the study of the global fluctuations. So that is, we're looking at all the particles together and computing some averages over all the particles. That was our law of large numbers and this kind of central limit theorem. So what will come next, instead, we'll be looking individually on the particles. Maybe you want to say something about spacing of the particle. Maybe you want to say something how your configuration looks locally here, or maybe here, or maybe here. And this will be the kind of questions that we will be addressing. Like what's happening with the same uniformly random tiling, but now locally, when you zoom in near one of the points. And that's, these and related model, that will be the topic of the remaining 2 lectures. So thank you. So see you on Tuesday. Christian, I've lost the name of this guy that you told me about the hexagon. So can you tell it to me again? So the hexagon with the hole. Remember we were discussing the hexagon. I want to write it for myself in electronic form. Otherwise, it's